This video is on electric field lines and parallel plates. Question 1. Define electric potential difference. Is it a scalar or a vector? What are its units and fundamental units? Electric potential difference is the work needed to move a charged object between 2 points when it experiences an electric field. So electric potential difference is a scalar. It has units of volts or joules over coulombs. And remember, a joule is kilograms meters over second squared. Kilograms meters squared over second squared, and a coulomb is equal to an ampere second. So imagine the electric potential difference needed to bring a proton from point 1 to point 2, or an electron from point 2 to point 1. Question 2. What are the units and fundamental units of voltage? It's joules over coulomb. Remember, joules has units of kilograms meters squared over second squared, and coulomb has units of amperes times second. Question 3. Define electron volt. This is the energy given to an electron by accelerating it through 1 volt of electric potential difference. So imagine this electron going from the negative plate to the positive plate, and it accelerates. So it's common to convert 1 electron volt to joules and joules to an electron volt. Question 4. List some rules for drawing electric field lines. So electric field lines tell us the direction a positively charged object will move when it is in an area of electric charge. So electric field lines always point from positively charged objects to negatively charged objects. Electric field lines are always perpendicular to the surface of a charged object. The number of electric field lines is directly proportional to the net charge of the object, and there are no electric field lines inside an object. Electric field lines never cross other electric field lines. You should compare these rules to the rules of gravitational field lines from an earlier worksheet. Question 5. Draw electric field lines for each figure. So if you have this positive charge, the electric field lines are the lines with arrows. For a negative charge, the electric field lines are the lines with arrows, and they go towards the negative charge. If you have a positive and a negative charge, remember, electric field lines tell us the direction a positive charge moves. So the positive charge repels the positive charge, and the negative charge attracts the negative charge. If you have 2 positive charges, you could see the electric field line looks like this. Remember, electric field lines are the lines with the arrows. Question 6. Use a pencil and ruler. Draw charged parallel plates. Looks like this. These plates are equal in magnitude, opposite in charge. Part B. Draw and label 6 electric field lines between the parallel plates. Remember, the electric field lines tell us the direction a positively charged object moves. So the positively charged object moves from the positive side of the parallel plate to the negative parallel plate. Part C. If a positive charge is placed between the plates, then in which direction will it accelerate? Well, it accelerates to the right. In part D, if a negative charge is placed between the plates, then in which direction will it accelerate? It accelerates to the left. Part E. Which variable is constant between charged parallel plates? It's the electric field. Part F. Define each variable for the equation for parallel plates. V equals ED. V is the potential difference between the 2 plates. It has units of volts. E is the electric field between the 2 plates, has units of newtons over coulomb. And D is the distance between the 2 plates, has units of meters. Question 7. A charge of 15 microcoulombs is placed in a uniform electric field which has a field strength of 8.8 times 10 to the 4 newtons over coulombs. Part A. What will be the magnitude of the electrostatic force acting on this charge? Well, F equals QE. Part B. How much work will be done in moving this charge a distance of 135 centimeters against the electric field? So W equals FD. Part C, what will be the potential difference between these 2 points? So V equals ED. So this is a uniform electric field, and parallel plates have a uniform electric field. So we could use this equation. Question 8. A proton is placed at point A in a uniform electric field which has the field strength of 4.5 times 10 to the third newtons over coulombs, and which is directed towards the top of the page as shown in the diagram below. Part A. What will be the direction of the electrostatic force acting on this proton while at point A? Well, these electric field lines always point from a positively charged plate to a negatively charged plate. So imagine that there's a positive charged plate on the bottom and a negatively charged plate on the top. So if you put a proton at point A, the proton is going to move upwards. Part B, what will be the magnitude of the electrostatic force acting on this proton while at point A? Well, F equals QE. Part C, how much work will be done in moving this charge a distance of 12 centimeters against this electric field to point B? So work is equal to Q delta V. V is equal to ED. Part D, how will the electrostatic potential at point B in this field compare with the electrostatic potential at point A? Well, at B it's going to be greater than A, because if you put a positive charge at B, it's going to accelerate quicker than if you put a positive charge at point A. Part E, what will be the potential difference between points A and B? So V equals ED. And the distance between A and B is 12 centimeters. Suppose that this proton is then released and is allowed to accelerate back to point A. Part F, what will be the velocity of this proton when it returns to point A? W equals Q delta V, which is equal to delta E sub K. Solve for V final. So this should be V final, not V initial. Suppose that the proton is again at rest at point A. How much work will be done in moving this proton from point A to point C? It's 0 because it's at an equal potential surface. Hopefully we'll learn more about equal potential surfaces later, if we haven't learned about it already. Part C, how will the electrostatic potential at point C compare to the electrostatic potential at A? They're both equal to each other. Part I, what will be the potential difference between point C and point B? It's going to be equal to that of A and B. Part J, how much work will have to be done on a proton to move it from point C to point B? It's going to be this. Question 9. Two parallel plates are arranged as shown below. The electric field between the plates is uniform and is directed from the positive plate to the negative plate. The electric field strength is 6 times 10 to the 4 Newton over Coulomb, and the two plates are 6 centimeters apart. A particle which has a charge of negative 0.0150 microcoulombs is initially placed at point A. So if you have a negative charge at point A, it's going to accelerate towards the plate. Part A, how much work will have to be done to move this particle from point A to B? We're going to use this equation. Part B, what is the potential difference between A and B? Well, V equals ED. Part C, how much work will have to be done in moving this particle from A to C? The work done from A to B is going to be equal to the work done from moving from A to C. Part D, what is the potential difference between point B and C? Well, B and C on an equipotential surface, so it's going to be 0. Suppose that another particle with a charge of 2 microcoulombs is placed initially on the negative plate. This particle is then moved from the negative plate to the positive plate. Part E, how much work will be done in moving this particle from the negative plate to the positive plate? We use this equation again. What will be the potential difference between these two plates? V equals ED. Question 10. A proton, which has a mass of 1.67 times 10 to the minus 27 kilograms and a charge of 1.6 times 10 to the minus 19 coulombs, is moving with a velocity of 5.6 times 10 to the 6 meters per second from left to right into a uniform electric field as shown in the figure below. The electric field has a magnitude of 5.6 times 10 to the 5 newtons over Coulomb and is directed upward, as you can see. So, if this object is positively charged, it's going to curve upward. Yeah? It's going to curve upward. Part A, what will be the direction and magnitude of the gravitational force acting on this proton? F equals mg, force of gravity. It's going to be downwards because force of gravity pulls it towards the center of the earth. Part B, what will be the direction and magnitude of the electrostatic force acting on this proton? F equals to QE. And that's going to be upwards because this is positive charge and it wants to go towards the negative charge. Part C, what would be the direction and magnitude of the net force acting on the proton? Sigma F, you add up all the forces. Part D, what will be the direction and magnitude of the acceleration of this proton? Remember, F equals ma. Part E, what will be the velocity of this proton 1.25 microseconds after entering the electric field? So we got V sub x, we got V sub y, and we could find V, and we could find theta. Part F, what would be the displacement of this proton 1.25 microseconds after entering the electric field? So we got x sub f here, we got y sub f here, we could find s and theta. Question 11. An electron which has a mass of 9.11 times 10 to the minus 31 kilograms and a charge of minus 1.60 times 10 to the minus 19 coulombs enters a uniform electric field with a velocity of 5.8 times 10 to the 7 meters per second. The electric field has a magnitude of 2.9 times 10 to the 4 newtons over coulombs, is pointing vertically downward, and is contained within a limited area. The dimensional units of the electric field is 35 centimeters horizontally and 22 centimeters vertically. The electron enters the uniform electric field horizontally from the middle of the vertical. The force of gravity also acts on the electron. So part A, sketch the path of this particle through the electric field in the image above. Remember, this is negatively charged. Above here we have a positively charged plate, and below here we have a negatively charged plate, because the electric field lines always go from positive charge to negative charge. So this electron wants to move upwards towards a positive charge. Part B, what will be the net force acting on this electron? It's going to be this. And it's positive, so it's going to be upwards. Part C, how long will it take for this electron to pass through this field? So the horizontal speed is constant. So it's like this. Part D, where exactly would the electron exit the field? So this is the vertical distance traveled. And the horizontal distance traveled is 35 centimeters. Part E, what will be the velocity of the electron as it exits the field? Well, we got V sub x, we could solve for V sub y, then we could take the magnitude, and we could get theta.